Did you know that swamp microbes have evolved to live off all kinds of decaying matter? They can digest almost anything, like tree stumps and even bone fragments. They tend to be slowed down or stopped in their tracks by some of the new man-made synthetic materials now referred to as forever chemicals. These substances are now poisoning us, and unfortunately, we don't have time for microbes to learn how to digest these nasty compounds.
Blobby dear, please finish your sewage.
But Mom, I need time to evolve before I can eat this stuff.
Hi, I'm Lenny Rome, the Vault Guy. I'm a cell biologist and a nanotechnologist. My passion is a common particle of the human cell called a vault. My goal is to explain what vaults are to non-scientists. In my last video, I wrapped up my discussion of engineering of vaults for cell delivery. If you haven't seen it, I'll put a link below. Today, I want to begin the first of 3 episodes dedicated to the engineering of vaults to aid in environmental remediation of chemical contaminants. I'll be covering 3 things. First, I'll try to explain current soil treatment methods and why biological methods might have advantages. Second, I'll tell you about BPA and related reproductive toxins. And finally, I'll tell you about our efforts to make a vault that can chew up these toxins. Stick around, and I'll introduce a former graduate student who is the real star of the next 3 episodes. Around the time we were working on engineering vaults to package enzymes inside, I thought about our early efforts to clone the MVP gene in the common slime mold Dictyostelium discoideum. I mentioned this in episode 7. Slime molds are an important soil organism that feed on decaying matter, bacteria, and other microorganisms, and they have a crucial role in breaking down organic matter and releasing nutrients that plants need. And every slime mold cell contains tens of thousands of vaults. I began wondering if it would be possible to engineer a slime mold so that its vaults could harbor an enzyme within that could degrade some environmental contaminant. That way, in addition to assisting in recycling of nutrients, the slime mold could also contribute to cleaning up man-made messes in the environment. I didn't have any experience in this field, but one day after attending a seminar in the California Nanosystems Institute, I met an environmental engineer named Shally Mendra. Shally is a professor of civil and environmental engineering in the UCLA Samueli School of Engineering. Shally, turned out, was the ideal person to discuss ideas about engineering vaults to degrade some undesirable environmental contaminants. She was very interested, but one of the first things she did was pour cold water on my simple idea. She informed me that the Environmental Protection Agency, the EPA, doesn't allow engineered microorganisms like slime mold to be introduced into the soil, as they can reproduce and cause unforeseen consequences. However, she did think that if we could engineer vaults to contain a degradative enzyme, then we could just try adding the vaults, which don't reproduce, to the soil. I had a lot of misgivings about this direction, since I was worried that the vaults would be unstable. But nonetheless, I did think it would be interesting to at least give it a try. Shally's lab was working on ways to clean up environmental contaminants in soil and in water. One of the chemicals she was trying to control was bisphenol A, abbreviated BPA. BPA is an additive used in production of plastics, epoxy resins, copy paper, PVC, dental sealants, flame retardants, and food packaging containers. BPA can leach out of the products it's used in. This is a serious environmental problem because BPA has been shown to be a reproductive toxin. Many environmental activists are against the use of BPA, and they point out that it's even in the plastic bottles used to feed formula to newborn babies. Shally told me about the various ways available to degrade BPA. These include physical, chemical, and biological treatments. The problem is that most current methods are expensive, inefficient, and often generate toxic side products. Environmental engineers like Shally are focused on biological treatment methods because they generally cost less and require less energy. You can use microbes to degrade environmental toxins, but the process is time-consuming. The microbial cells might not stay healthy in contaminated water, and there are significant public health concerns with releasing microbes, which might cause diseases, into the environment. Enzymes isolated from microbes, on the other hand, work faster, have less dependency on the water chemistry, and do not cause public health concern. The biggest problem with using enzymes is that they don't last very long in contaminated water or soil because they are just not very stable. To overcome this limitation, engineers have tried to increase the stability of enzymes by binding them to or trapping them inside different inert materials. This process, called immobilization, can be problematic as well, as it often deactivates and denatures the enzymes. It limits the ability of the enzyme to find its target, and thus it prevents the breakdown of contaminants. Shally and I wanted to test if immobilization of an enzyme by packaging it inside a vault might preserve or even improve its properties. Enter the star of this story. Shally assigned the project to a very resourceful graduate student named Meng Wang. We taught Meng how to make vaults in the baculovirus system. His first project was to select an enzyme to serve as a test case. He chose manganese peroxidase, MNP. Peroxidases are a class of enzymes that can act on a wide variety of chemicals, including organic dyes, explosives, fire retardants, and chemicals, including BPA. Peroxidases act by introducing oxygen using hydrogen peroxide as a co-reactant. This process is called oxidation. Meng engineered the manganese peroxidase gene from a fungus to express a fusion protein between MNP and INT, the vault packaging domain that I have told you about repeatedly. He expressed the MNP-INT fusion protein in insect cells and first showed that the fusion protein retained its enzymatic activity. This step was not something that was automatically expected to work, as enzymes are exquisitely dependent on their three-dimensional structure for their catalytic activity. Fortunately, the MNP-INT fusion protein was every bit as active as the native MNP enzyme. Meng then packaged the fusion protein into vaults. The vaults containing MNP-INT also exhibited MNP activity, and surprisingly to our delight, the vault packaged MNP had even better enzymatic properties than the free enzyme. In other words, the enzyme packaged into vaults degraded BPA faster than free enzyme, and it also worked at higher temperatures. Meng also compared the vault packaged enzyme to free enzyme for degrading two other nasty chemical additives related to BPA called BPF and BPAP. The vault packaged enzyme was more active toward each of these chemicals. Finally, he used a common model organism to show that unlike free enzyme that converts BPA into products that are still reproductive toxins, the vault packaged MNP degraded BPA into products that were no longer toxic. We were really pleased with Meng's results, but we still had two serious hurdles to overcome. First, if vaults were ever going to be helpful for environmental uses, we would need a system for making vaults that could be scaled up for commercial production. The baculovirus system was expensive, and although it was being used commercially for making vaccines, it was unlikely that it could be scaled up significantly further. The second problem was that even though vaults protected their cargo, we still needed a way to protect the vaults themselves. Meng was determined to go after both of these issues. I'm Lenny Rome, the Vault Guy. Join me in my next episode where we tackle the vault production problem. We could make milligrams of vaults, but would we be able to make pounds or even tons of them? As always, like and subscribe, and please comment on my lessons.